Okay, so we're going to pick back up here and work some problems and determine which points are the functions continuous. So if we're given a function, our f of x is equal to 1 over x plus 3, the first thing we need to do is figure out where it's discontinuous. Okay, well, that's going to be where the function's not defined and we know our denominator can't equal 0. So yeah, so we're going to subtract x cannot equal negative 3, or we would say in this case it's discontinuous. Discontinuous at what? X equals negative 3, right? So that's all the same way to say that. But what was the question? Where is it continuous? Well, if we know where it's discontinuous, then we know where it's continuous, right? So if we wanted to think about a number line, some people do better with this if they put it on a number line and say at negative 3 it's an open circle, but it's continuous everywhere else, right? So tell me how I would describe that in interval notation. Continuous at negative infinity to negative 3, either a parenthesis or a bracket. Absolutely. Or it picks back up at negative 3 and goes to infinity. So the answer is this. Careful, because if it asks you which points are discontinuous, we would give this solution. If it asks where it is continuous, we would give this interval notation. Okay, so this is a rational function. This one is a polynomial. It doesn't have any discontinuities this term, so we're just going to identify where it's discontinuous in the first term, which would be what? So x minus 5. Yeah, we can do this. We don't necessarily have to. You've done this enough that we can say discontinuous at x equals 5, right? So continuous at, give me interval notation. Negative infinity to 5, union 5 to infinity. Good. Two very basic ones. All right, what about 3? What's the only difference? We probably need to factor this out, right? So we'll take that. And I'm going to give you a minute to factor it and determine where it's discontinuous first. So pause it and do that one on your own. Correct that. Take that squared off right there. Okay, so now x squared minus x minus 20. Okay, so it's discontinuous at 5 and discontinuous at negative 4. Now, interval notation for that, and it may help you to draw a number line like we did up here, but give that to me. You would go from negative infinity to, which one of these come first on the number line? Good, negative 4. And then we'll pick back up at negative 4 and go to 5. Good. And then we would pick back up and go from 5 to infinity. Good. Okay. Y equals x plus cosine of x. Nothing there. And what about cosine of x? Cosine of x, right? It's just our continue in both directions. So is it discontinuous anywhere? No. What about x? It's not discontinuous anywhere. There's no issue. So what will we say about 4? Continuous at, let me put it in blue. How do we describe everywhere? Negative infinity to positive infinity. Good. No discontinuities are happening there. What about this? It's rational, so what's the place that it's discontinuous? Yeah, it's discontinuous at x equals 0, so continuous. Discontinuous at x equals 0, so you can make that note. So continuous at, give it to me, negative infinity to 0, and then 0 to infinity. Good. Okay. All right. Define f of 2 for the given function so that it is continuous at x equals 2. Okay. First of all, let's factor this out and see what happens. Let me pause it and do that. Okay, so when we have that, these cancel, and that just means we have a removable discontinuity okay, spell that wrong. Discontinuity at x equals 2. Okay, so we've done this previously. We've done that a lot. You just didn't know it for what it was. So today we looked at the image of that, and it's just a removable discontinuity at that value x equals 2. So typically we evaluate the function. When we were doing this before, we would take the limit of the function and evaluate it at x plus 5. Okay, so we can also evaluate f of 2. So let's do that just algebraically. Okay, when we plug that in here, what do you get? 2 plus 5, right? So what's 2 plus 5? 7. Good. So we would just say f of 2 is equal to 7. So you can define f of 2 as 7. So if we would have originally plugged in a 2, if we were taking the limit of this function as x approaches 2, and we would have used direct substitution, we would have got 0 over 0, which we would have simplified factoring. This removable discontinuity lets us still be able to evaluate the function. And in this case, we evaluate f of 2 using the simplified form and just get 7. Okay, we're going to practice a few more examples for what values of x is f of x continuous. So 7 and 8 should be pretty intuitive to you. We've done those previously, so I'll let you pause this and try it yourself and then check your answer. 9's going to be something new, so we'll work that one together. But go ahead and check yourself on 7 and 8. Okay, so factor this trinomial, solved for it not equal to 0. So x is discontinuous at 3/2 and -1. So we would state our interval of continuity to be negative infinity, -1, union, -1 to 3 over 2, union 3 over 2 to infinity. And polynomials continuous on all the real numbers. All right, if you remember when we talked about the domain back in pre-cal of a radical, what did we do here? We would take this and set it greater than or equal to 0. Why greater than or equal to 0? To guarantee that it's positive, and that's exactly what we did. So in that case, we would just set x squared plus x minus 6 greater than or equal to 0, and then we factor here. What multiplies to give us a -6 but adds to give us a +1 would be x plus 3, x minus 2. Okay, so we're working with the values -3, x equals -3, and we have x is equal to 2. Check on. Okay, so I know my values of discontinuities are in this case we want to guarantee that it's positive, so it's greater than 0 at the values -3 and 2. So if I were to put those on a number line, I'm going to have that close circle, close circle. Now because this is an inequality, I need to test the values to know where I'm going to shade this thing. Okay, I need to test my values to shade it. So let's test a value to the left of -3. So let's just pick, let's test -4. Okay, plug -4 into x everywhere that you get that. So test, let me give myself some more room. Let's test -4, so I'm going to have square root of -4 squared plus -4 minus 6 greater than or equal to 0. So let's simplify that. That's going to just give us 16 minus 4 minus 6, which is what? Square root of 6. Is the square root of 6 greater than or equal to 0? True or false? True. So the region I tested to the left of this mark is true, so I'm going to shade this to the left. Okay, let's test this middle region. What's an easy number in the middle of these two to test? 0, yeah, so let's just, now understand we can choose anything, so let's test x equals 0. Same thing, so that's going to be 0 squared plus 0 minus 6. So square root of -6 is greater than or equal to 0. True or false? False. So we do not shade that region of the graph. So we do not shade here. Now let's test just to the right of 2. Let's just test x equals 3. So 3 squared plus 3 minus 6. 1 plus 3 is 12 minus 6. Square root of 6 greater than or equal to 0? True. Okay, so that means shading here. So that's everywhere that is continuous. So describe those regions to me that we graphed in the number line. So continuous, we'll now say continuous at what? -infinity, -3 with a bracket this time, union. Oh, and then it's going to pick up where? Bracket 2 to infinity.